All right, good morning, everyone. So, we already finished off yesterday, so we were talking about Archimedes Principle. So again, Archimedes Principle says that any object which is partially or fully submerged within some sort of fluid feels a net upward force, called the Buoyant Force, whose magnitude is equal to the weight of the fluid which is being displaced. So here, this is my object, whether it's partially or fully submerged, doesn't really matter. What it feels is upward force, which is then equal to the mass of the fluid being displaced times g to make it to the weight, which is then equal to the density of the fluid times the density, times the volume of the fluid, times then g. G again is the acceleration due to gravity. So this is our buoyant force. So we did a couple examples yesterday, but let's do one more. So let's actually look at the historic reason where this actually came about. And this came about by the fact that Archimedes was tasked by the king to determine if a crown that he was made or was given to him was made out of pure gold or not. This is actually where this idea actually came from. So Archimedes kind of later on, he was trying to figure out how he could actually determine this. So apparently the story goes that one day he was in the bath, and when he got into the bath, he noticed that when he went into the bath, that the water actually displaced, and it displaced exactly about the volume at which it was that he went into it. And then he used that to come up with the Archimedes Principle, at which stage he ran around the entire city, butt naked, screaming, "Eureka, Eureka! I solved the problem." That's basically what it was. So from there, what he decided to do was an experiment to then determine exactly what the density was. And then from the density, if he knew the density, then he could determine the material which it was made out of. And then from there, the king could decide if he wanted to kill the guy or not. Because if it wasn't made out of gold, like he told him, off with the head. But if it was made out of gold, the guy gets the lid. Life is great. So what he did was decided to first measure the weight of the crown outside of a fluid. So basically air. So basically, here's my crown. Right, so let's say here's my crown. And then he attached a string to it, and then basically measured the tension on the string. So initially, what this means is he's going to measure some tension. So initially, he measures the tension to be 14.7 kilograms times g. Okay? So we just measured that the mass of this thing was 14.7 kilograms times g. So that then is equal to the tension. So in this case, the tension is simply equal to the weight of the object. Okay, we got mg down in this direction. So that means this is also equal to 14.7 kilograms times g. Then what he decided was, okay, let me take this same situation, but now let's put it inside of a fluid, primarily water. So here's now my crown. He's going to now fully submerge this inside of a fluid. So this now has the density of the fluid, which is equal to the density of water. And again, measure the tension. So now let's measure the tension in the string. So what's going to happen? Well, the tension in the string is going to reduce. So what he finds now is that the new tension, let's call that T prime, is now equal to 13.4 kilograms times G. Which means that what he's actually measuring here is now what we call an apparent weight, which means he's measuring a new mass for this thing, which is now equal to 13.4 kilograms is now the new mass times G. So if he submerges it in a fluid, what we know now is that there has to be a buoyant force pushing upward. That buoyant force then adds an extra force, which is actually pushing upward, which means then that the reduced tension that he's measuring is reduced by the amount of the buoyant force. Okay with this? So his observation then was if I take the tension when it's outside of the fluid, minus the tension when it's inside of the fluid, well, that must be equal to simply the buoyant force. Because here, there's no buoyant force. There it is, but very small. But in this case, we have the buoyant force from the fluid pushing upward, which means that there's two forces up in this direction, which means if I take this guy minus this guy, the difference between the two is then equal to the buoyant force. Okay? Good. So from here, we now know that the buoyant force is simply equal to the mass of the fluid being displaced times g, which is going to be the same thing then as the density of the fluid times the volume of the object, since it is fully submerged within the fluid, times then g. But now if I go back to this picture, what I know is the tension here is simply equal to the weight of the object. So the tension by itself, which means the tension is equal to the weight of the object. I'm going to say the mass of the object times g. But in terms of density, this is the same thing as the density of the object times the volume of the object times g. So now, if I want to know what is the density of the object, well, I can get the density of the object by dividing these two things out. So if I simply take this result here and divide by this result, I can then get a ratio of the two densities. So let's go ahead and do that. So if I take the tension minus the tension prime, so the tension in the fluid minus the tension out of the fluid, and divide that by the tension out of the fluid, then this must be equal to then the density of the fluid times the volume of the object times g divided by the density of the object times the volume of the object times g. Well, what happens to those two volumes? They cancel. What happens to the two g's? They also cancel. Which means I never have to know the volume of the object. The only thing I need to know is the density. So finally what this says then is I can determine the density of the object by knowing the density of the fluid. So if I put this in water, I know the density of fluid, that's 1,000. And I know the two tensions. So finally what I can say then is that the density of the object is equal to the density of the fluid times the ratio of the tension out of the fluid minus the difference between the tension in the fluid and out of the fluid. Okay? So what I know is that this is equal to 1,000 kilograms per meter cubed times tension out of the fluid, which is then 14.7, divided by 14.7 minus 13.4. So finally, what I find then is that the density of the object is then equal to 11,300 kilograms per meter cubed. So from here, all I then have to do is look up what the different densities of different materials are. So for example, what I know is that the density of gold is equal to 19,300 kilograms per meter cubed. And I know the density for lead is equal to 11,300 kilograms per meter cubed. Which means now I compare the density at which it is that I measured using my Archimedes principle versus at the density of gold. This density is much less than that of gold, so I know it can't be gold. But then I match this then to the lead, which means that my crown is actually made out of lead. Gold plated. What happened to the poor guy that made it? He's dead. Head is now chopped off. Okay. So, Archimedes principle. So yeah, every object partially or fully submerged in a fluid must feel a buoyant force. That buoyant force is equal to the mass of the fluid being displaced. So again, not the mass of the entire fluid, but only the fluid which is being displaced, which is then equal to the density of the fluid times the volume of the fluid times g. So that's my Archimedes principle. So the poor guy died. So shouldn't have died. Everything okay? So that brings us to group assignments for today. We'll move on to new material after this. So I have two problems for you today. Both of them involve Archimedes principle. So the first one says that we have a cube of side length 10 centimeters made of an unknown material floats at the surface between water and oil. So basically what happens is oil has a lower density than that of water, so we know based off of Archimedes principle it has to float then on top of water. That's what we talked about yesterday. So we know that the density of oil is 810 kilograms per meter cubed. Now what happens is when I put in this unknown material, 72% of it I find floating inside of the water, and then the remaining 28% of it I find floating in the oil. So from there, what I want to know then is what is the mass of this unknown cube, and how much buoyant force is actually acting on this one. Now, when I draw this out, I'll point out to you there's actually two different buoyant forces in this case, but we'll be there in a second. So that's the first one. So the second one then says we have a block of wood, has a mass of 3.67 kilograms and a density of 600 kilograms per meter cubed. It is loaded with lead, which has, in this case, 11,400 kilograms per meter cubed for a density, so that it will float in water so that 90% of the wood is submerged under the water. So only 10% of the wood is not submerged in the water. So what I want to know is what is the mass of the lead needed that 90% of the wood is within inside of the water if the lead is attached on the top of the wood for part A, and then if the lead is attached on the bottom part of the wood for part B. So let's draw these pictures. Let's kind of see what each one of these is asking. Where am I here? So let's draw a picture for each one. Problem number one, all this means is I have some container. Inside of that container, I then have water here. My density of water. And then somewhere above that, I have oil. I draw the oil in yellow. This is my oil, so I have density of oil. Now what this thing says is I'm going to put a cube inside of here so that the cube floats at this interference part between the two, so my interface, so that it's doing something like this. So here's my cube, where I know this has a side length of L, and I know that this amount of here is 72%, and the rest of it that's up here is then 28%. So this is my picture. So notice here, if I'm thinking about a free body diagram, which is what I should be thinking about, I have the weight of my object downward, right? So this is the mass of the unknown times g. But in this case, I have two different buoyant forces pushing upward, right? I have one buoyant force from the water, because the water wants to buoy it upward. But there's also another buoyant force from the oil also trying to push it upward. So I have two different buoyant forces. So in this case, I'm going to have one buoyant force, this one, pushing on F of B from the water. And then I'm going to have a second buoyant force, use red, acting on this portion of it, which is the buoyant force from the oil. So when I'm drawing my free body diagram for this case, I have to make sure I take into account both of those two different buoyant forces. So from there, do the same thing we did yesterday. Sum of the forces is equal to 0. From that, find the mass, and then find the buoyant force. So the buoyant force in this case is simply going to be the sum of these two buoyant forces. That's the total buoyant force. Part 2, or question number 2 then says, we're going to take that this thing is floating in water, right? Yeah, water. So here's my water. I'm going to put my wood inside of here. So here's my wood. So that this portion, which is submerged inside of the water, is 90%. This is true for both parts A and B. Now, what part A is saying is I want to make sure I put lead on this such that the lead is going to be on the top portion of the wood. So all that means then is for part A, I'm loading that a chunk of lead is going to be up here. So those are going to be lead. So what I want to know in part A is what is the mass of that lead? So how much mass do I have to put in the lead to make sure that only 90% of the wood is submerged within inside of the water? So that's part A. Part B then says, now we want to load a little lead on the bottom. So that now this is our lead. So I want to know what is the mass of this lead down here. So essentially, what's the difference between part A and part B? What's the difference between part A and part B? Part A, how many buoyant forces do I have? 1. Right? I got 1 coming from the water onto the wood itself. That's my only buoyant force. So in this case, I have 2 different weights down. I have the weight of the wood, I have the weight of the lead, but I only have 1 buoyant force, which is acting on the wood. What's different in part B? How many buoyant forces do I have? Math. 2. So what's different now is I still have those two masses, so I still have those two weights downward, but now I have a buoyant force onto the lead and a buoyant force onto the wood. So the difference between A and B is the location is different, which then determines the number of buoyant forces that I have. So part A, I have one buoyant force only on the wood. Part B, I have a buoyant force on the wood and a buoyant force onto the lead. So part A, I have 3 forces. Part B, I have 4 forces. That's the only difference. Ultimately, you do exactly the same thing. Draw your free body diagram, label your forces, sum of forces is equal to 0, and then solve your existence. So, give about 15 minutes to work on these. Just kind of get started on them. And we'll spend the last 10 minutes talking about non-static fluids and start talking about dynamical fluids, so fluids which are in motion. And these guys are already on my blackboard, so. Don't mind a man behind me. What's that?
What does the PV stand for again?
Lead. Yes. PV is the, I forget what you call that. Elements. There you go. AU is gold. The laptop won't be here on Monday, so we'll have to move over. Good. Good. Yes. So you can write them in terms of the total volume. So, for example, good. So here you can write that the volume of the wood is equal to 0.9 times the volume of the object. Oh, sorry, 0.72. Sorry. I still have a problem. Yeah. So let's not worry about the 10. Just write it as volume. So this one is going to be 0.72 times VO. Then this one is going to be 0.0, so that's going to be 0.28 times VO. So that way all your VOs are also the same. So you can actually cancel out quantity objects as well. So that's a good one. All your VOs are going to cancel. Okay. And then in this case, what do you look for? The mass. So you can find the density and then find the mass from there. Yeah. Okay. And now you know all the. The only thing you don't know now is the density of the. Well, it's not wood. Remember, that's water. Well, the rock is made of another material. So that density is the same as this density. Oh no, sorry. Yeah. So you know the density of the water, you know the density of the oil, you just don't know the density of the. Correct. Yeah. And then once you have that, then you just multiply it by the volume of the object, and then it's the mass of the object. So.
That's right. Going on with numbers now.
You can leave it as the mass of the object, or you can solve for the density of the object and find the mass. Either one is solved. Well, because you told the it's a cube at length size, so it's just 0.1 meter. So you can rewrite the volume of the oil in terms of volume. You know, 72% is water, which means the volume of the water displaced is 0.72 times volume. So yeah, so the volume in the water is 0.72 times the volume of the object. Okay. And then the volume of oil is 0.28 times the volume. And then you know all the densities and everything. Is that right? Yeah. One's on question. The second one. Okay. You do part A.
Yes. I have.
Good. And now that's equal to 0.
Yes, but I have a question.
Sure.
This should be the density volume over here for each one.
Right. Yes. Yes.
They're giving me
Because
the
you know the density of the wood, you know the mass of the wood as well, but you also know the volume. So yeah. So right now it's probably easier to write it in terms of density and volume.
So do I have to solve the volume here?
Solve for volume.
Because I have already.
Right. So ultimately, what you know is right. So to find the mass of the lead. So I never told you the volume of the lead. So basically what you're going to do is you're going to rewrite the mass of the lead as being the density of the lead times the volume of the lead.
Mhm.
And then from there, what can you do from there? So it depends on how you want to approach it, but the easiest way to do it then would be to rewrite the volume of the lead in terms of the mass. Because the mass, so remember that density is equal to, or sorry, mass is equal to density times volume, which means volume is equal to mass divided by density.
So do you think that I have to
Well,
rewrite this
it's
one?
going to be rewritten here because the volume of the fluid, which is being displaced, at least for this part, it doesn't matter. But for the
Yeah.
next part, I'm thinking about is one of the other one. But yeah, no, for here, you're going to solve directly for the mass of the lead.
Okay. Because I was thinking about that, but is this correct, right?
Yes. Yeah, because you have the 1 force upward. So this is actually kind of that guy. That's right. Yep. Okay, that's right. Yep. Well, be careful, there's two buoyant forces here, right? So there's one from the water and one from the oil.
Yeah, I just do that one. Is this right?
Well, you can't do one at a time, right? Because you have to consider the object as a whole.
Okay.
So as the entire object is concerned, then basically there are both of those two forces pushing it upward, so not just one. So you can't just do sections of it, you have to do the entire thing. Okay. So from here, the only thing you'd want to do then is add the buoyant force from the oil. Okay. Yeah. So just add that one extra piece. Okay. So you're missing a 0 here for the volume, right? Yeah. Because it's 0.1 times 0.1 times 0.1. Because it's cubed, not just squared.
It's still not to that.
So then that was the density. So
Yes.
oh, okay. The problem is that should be 28, not 72. Because it's only 28%. Good. So I want you to do that initially.
I just want to see that, you know, it's right. So, the total, so I added the piece together, but did I set this up? The fun, volume of the oil. I'm going confused.
No, no.
So,
Where did the 28 come
the quantity is 28% on top.
Oh, well then that's not the volume of the cube then. So the volume of the cube is just 10 times 10 times 10.
Oh, okay. So then you use volume of water instead of oil? Or-
Well, no, you have to use the volume of the cube for the other side.
Oh, I see, okay.
Right. So what all that's equal to.
Okay, and then your G's would cancel.
Correct. Exactly. Okay.
I saw for example, I see that you are giving the mass and density of the wood.
Yes.
Why if I'm not using the mass of the wood?
Well, you could. Yeah. So at this
I
stage,
mean, I
you could
could use this one
Yeah.
instead of there.
Yeah.
But how can I do this with the density of the fluid?
Right. Well, this is what I was saying earlier. So the density of the fluid then is going to be equal to what? So it's going to be. Let's go back to our picture. It's 90% of the volume of the wood. So we know that the volume of the fluid is simply 0.9 times the volume of the wood.
Okay, you move it like this. That's it.
So now you need to know the volume of the wood.
Oh, yeah.
So where's the volume of the wood going to come from? Well, again, we know that the mass is equal to the density times the volume, which means the volume is then equal to the mass divided by the density. So that means the volume of the wood is simply going to be 3.67 kilograms divided by 600 kilograms per meter cubed.
Okay.
So that's going to give you that, and then the volume times 0.9 is going to give you the volume of the fluid.
So it will be like this.
Yeah, times the density.
Okay.
That's it.
Oh, okay.
So when doing the other side, you did the density of the volume revenue or?
Over mg? Yes.
Okay, so then now I'm getting just the density that I had there.
Well, once you find the density of the cube, then you would just multiply by the volume of the cube to get the mass.
Okay.
So those are going to come into, so the volume of the water is then going to be 0.72 times the volume of the object. Because 72% of it is there. And then the volume of the oil is going to be 0.28 times the volume of the object.
So I had 0.28.
Well, you would have to rewrite this as 0.72 times the volume of the wood, or of the object. So it's not the volume of the water anymore, but yeah. So in this case, it's going to be 0.72 times 0.1 meters quantity cubed. Yeah, and then for the oil, it's just 0.28 times that.
Definition about this one.
Yep.
So if I let it, should go down on it.
Yep.
I'm taking questions back. Aren't you like 2 million forces?
Oh, well, remember, it's not pushing on the bottom of anything. So we're not considering normal force, we're only considering the weights which are pushing downward. So that means that the net weight downward would be the mass of the wood plus the mass of the lead times G. So that means the right hand side should be equal to subtracting, depending on how you're doing it. Good, so basically all it means is that the one single buoyant force is going to be equal to the net weight. The net weight is the sum of the two masses.
Okay, so mine, only 3 forces would be mg plus mpb plus f.
Correct. Yeah. With the appropriate signs. What's up?
Where should I put the value?
Oh, so that comes into when you're considering the volumes. Right? So the volume then of the fluid being displaced by the oil is then 0.28 times the volume of the object. And then by the water, the volume of the water being displaced is 0.72 times the volume of the object. So remember, when I'm considering these guys, these two volumes, then I know this volume here is simply 0.28 times the volume of the object. And this one is going to be 0.72 times the volume of the object. So when I'm considering just these two terms, it's okay. So right there, right? 0.28. 28. Good. Times the volume of the object. And then plus density of the H2O times the volume of the water, which is now going to be 0.72 times the volume of the object. And all that has to be equal to mg. Or you cancel out the g, so yeah. Good, so that's it. So now you know this volume is the same as this volume. So you can factor that out and then just multiply everything. Right, so you get a 0.28 times 810 plus 0.72 times 1,000.
So I found my now capacity 946,000. So
So let's take a look. So we have the density times the volume.
Oh,
So where did the 72, 720 come from?
so I had the volume of the cube being only 280. It's in the whole volume.
well, be careful of your units, right? Because that's in centimeters, but you need things in meters.
Okay, that's probably why.
So it could be 0.1. These two? Oh, the buoyant force. So the buoyant force is actually just equal to, so once you have that mass, just multiply by g and that's the buoyant force. Because the net buoyant force has to equal the net weight. Okay. Or you can just calculate each individual buoyant force and add them together. Why do the hard direction? All right, so we got about 15 minutes, so let's start talking about some dynamical fluids. This will be the last part of this chapter, so we'll have to finish this up on Monday. So far, all of these things that we've looked at have all dealt with just static fluids, right? So we looked at Pascal's, we were looking at static fluids, we were looking at Archimedes, that was a static fluid. All of these things just have static fluid. So what does a static fluid mean? So what a static fluid means is that it is a fluid at rest relative to a container. So what does that mean? So that means if I took my water bottle here and I walked across the floor, this is still a static fluid. And the reason this is still a static fluid is because the fluid is not moving relative to the container. The fluid and the container are both moving, but that doesn't mean it a dynamical fluid because the fluid itself is not moving relative to the container. So when I talk about a dynamical fluid or a fluid which is in motion, what we really mean then is that a fluid is moving relative to some sort of container. So basically, we're going to make a distinction between real fluids and ideal fluids. So for us, we're going to particularly look at is what's known as an ideal fluid. The reason for this is that realistic fluids, we don't really know how to actually deal with a realistic fluid. To really deal with a realistic fluid, we have to computationally solve things and make approximations and basically try to put it as close to an ideal fluid as possible. Right? So this is what we're going to focus on. It's actually what's called an ideal fluid. And this is different from a real fluid. Let's talk about how they're actually different from each other. From a real fluid. What would be like a real fluid? So let's say I had some sort of fluid, say water or some sort of gas, flowing through some sort of tube. Let's say here's my tube. Flowing, say something like this. Let's say it's flowing to the right. In a realistic fluid, what I would imagine then is what? Near the sides of the tube, I would have some sort of friction type term. Right? So what happens is as the fluid is trying to move through, there would be a friction basically between the walls and the fluid itself, which would cause the velocity of the fluid near the tubes to be very small. Right? So the fluid is rubbing against the side of the walls, which would slow it down, which means if I was looking at the velocity profile of the fluid inside of the tube, what I would find is that there's going to be barely any velocity towards the outside, if any. And then as it starts going closer and closer and closer to the center, the velocity then will increase, reaching its maximum velocity then at the center, and then again start to taper off and die down on the opposite side. So overall, my velocity profile would look something like this. So this would actually be like a real fluid. The friction, which would be a kinetic friction, which is causing basically this profile here, is in fluids what's known as viscosity. So viscosity basically tells me how viscous that this fluid is, which kind of tells me how thick it is and how easily it would have some sort of force acting onto it, right? So this would actually be a realistic fluid. Another thing would be is if I had some sort of obstruction inside of this tube, then if I looked at the velocity profile, what would happen then is in a realistic fluid, what's going to happen then is I'm going to get field lines, or what we call streamlines, which is talking about the flow of the fluid. So these guys here are called streamlines. These represent the velocity of the fluid. What happened then in a realistic fluid is I'm going to get basically things like turbulence. Okay, so what would happen is, depending on how fast this velocity was actually moving, it'd look all kind of nice and pretty in this section here. But then behind this actual object itself, these lines are basically going to scroll around, which is what we call turbulence. So this would be a realistic fluid. So this region here would be turbulence, which means that these velocity vectors, or these streamlines, would actually cross each other. So these guys would cross. Now, if I have velocities which all cross each other, what that means then is that some points within inside of this region would have multiple different velocities at different times. So these guys actually crossing each other means that we have multiple velocities at the same points, different times. This type of flow is what we also call non-laminar. So non-laminar basically means that the velocity profile of my fluid flowing through this realistic fluid would be time and position dependent. It would be different at different times and different at different locations. This means that it is time and position dependent. So this is what we would call a real fluid. So a real fluid is a chaotic mess. Because it's a chaotic mess, we would have to resort to computational approximations to try to figure out how things like turbulence and et cetera work. Nobody actually really knows how turbulence works. So even when you're flying in an airplane and you have turbulence, we've heard of turbulence before, nobody really knows exactly how it works because it's a chaotic mess. So we have to actually computationally approximate what this thing is actually going to do. So this is what we would call a real fluid. Now for us, what we're going to deal with is actually idealized fluids. We want to make this system as simple as possible. So for an idealized system, so this is a real fluid. So for an ideal fluid, we're going to look at something similar but not quite the same. So for us, if this was our tube, what will happen then is that our velocity profile would be constant everywhere across the tube. So there is no maximum velocity. Every location will have exactly the same velocity. Those would be our velocity vectors, our streamlines. Which basically means that we're going to ignore viscosity. The other thing is, if I had an obstruction inside of here, so this is now my obstruction, we're going to assume in this case then that our flow is not non-laminar, but it's actually called laminar. So what happened is that the field lines, or these streamlines, would simply go around the obstruction in a nice, gentle, easy pattern. So something like this. So this is what's known as laminar flow. So what laminar flow basically means is that the field lines here, these streamlines, are constant at all points and constant at all times. What this actually means is that the flow is constant. So it means it has exactly the same magnitude of velocity at all times. Also, this thing is not turbulent because these things never actually cross each other. So here, the streamlines never cross. Never cross each other. Which means that we're also going to have no turbulence to it. So this is laminar flow. Laminar flow means, again, is that the velocity is constant, but not only is the velocity constant, it also means that the mass and the volume will also be constant at all times, and the density. So another side effect of this is that the density, mass, and volume will all be constants. Unlike, again, in turbulence, where now the density as well as the volume as well as the mass are no longer constant over time. So these are just our constants. So this is what we're actually going to look at. This is what's known as an idealized fluid. So an ideal fluid. So when we're talking about fluid motion here, or dynamical fluids, we're going to be focusing on is that second one, these ideal fluids. So we're going to ignore turbulence, we're going to ignore viscosity, we're going to ignore all the things that are going to make our lives as complicated as possible. Not exactly realistic, but that's fine. As far as this class is concerned, we'll take it straight. Okay. One other thing we're going to ignore has to do with it here as well. We're going to say that our fluid is also irrotational. So one other thing here is we're going to say our fluid is irrotational. What does that mean? So what that means is, if I had some mass, let's say here's my mass, and here, if this was following one of the streamlines being pushed along by the water itself or whatever the fluid is, by the time it gets here, what will happen is it'll sit in a single location, and this guy's just going to simply spin. Because I have this turbulence going on back here. So this piece of mass, or this particle, is simply going to spin, but it's going to spin about its own axis. So it's just going to sit there and do this. This is what's called rotational. Irrotational means that this thing is going to go through here. It might rotate around as it's actually moving through, but it'll never actually just spin around its own axis. This is what's called irrotational. So we're never going to look at, again, this just has to do with turbulence. It's never going to sit there and basically just spin about its own axis. So this is called irrotational. So we're going to ignore that process as well. So I'm just going to go back to turbulence. So these are the fluids that we're going to look at. So the first thing we're going to look at is what happens if I had a fluid, say, going through a tube, but that tube changes size. So what happens in this case? So if I have fluid flowing down one tube and then goes into a different tube which has a different cross-sectional area. Let's say here's one tube that's attached to a second tube, where these two tubes have different cross-sectional areas. So this portion over here has a cross-sectional area of A1, and this one here has a cross-sectional area of A2. So If I'm looking at my streamlines, what will happen then is that my system will do something like this. These guys are going to get funneled down into here. These guys will also be funneled down into here. So these would then be my streamlines. So if I look at one particular point, let's say I look at this point, I'm going to call that point 1. What I'll find then is that at point 1, my streamlines have a particular velocity. Let's call that v1. Then at some other point, say over here, if I look at say this point, point 2, I'm going to find a different velocity v2. So what I want to know in this case then is how does v1 relate to v2? Which one's bigger? Which one's smaller? How do these guys actually relate to each other? So to do this, let's say I'm going to look at this entire cross-sectional area. So my fluid is going to start here at say time is equal to 0. Then after some time delta t, this fluid is going to move to this location here. Okay, so in a time frame of delta t, my fluid is going to start here along this plane and then move to some particular location over here, which means it's going to sweep out this volume here. Okay, so in a time frame of delta t, I'm going to sweep out some volume, let's call that v1. So initially my volume's here, in some time frame delta t, it's going to sweep out to this location. This is going to be some distance, let's call that delta x1, and that this thing has a volume, let's call that v1. In the same time frame of delta t, this fluid, which is at this plane here, is also going to move forward to some location over here in that same amount of time of delta t. So this is happening over this time frame of delta t, and this one is happening also from this volume here, sweeping out to this location over here. It's going to sweep out some distance, delta x2, sweep out this volume here of v2, all within the same time frame of delta t. Okay? Not too bad. Now, how does volume here, let me call that delta v1 instead, and delta v2, how do these guys have to compare with each other? So the amount of volume swept out by the fluid here, how does that have to compare with the amount of volume that has to sweep out here? Based off of our assumptions. They have to be the same. Because here, we're assuming that again, our flow is laminar, which means that the volume must be constant. Right? So as long as this time frame of delta t here is the same as the time frame of delta t here, the amount of fluid within inside of this region, delta v1, must be equal to the amount of volume of fluid inside of this region here. So what this tells me then is that delta v1 must then be equal to delta v2. The volume here is simply equal to the cross-sectional area A1 times the distance at which this has traveled, which is delta x. This guy's going to be equal to what? A1 times delta x1. Over here, this must be equal to A2 times delta x2. Since this is moving at constant velocity, since it's laminar flow, this is also moving at constant velocity since it's laminar flow, and what I know is that delta x1 is simply equal to the velocity times the change in time. So I'm going to rewrite this then as a1 times v1 times delta t. And this must be equal to then a2 times v2 times delta t. Okay? From here, I can look at now what's called how this thing compares with time. T divided by t, which means the two delta t's are going to cancel. This tells me that a1 v1 must then be equal to a2 v2. So the pure fact that we're dealing with laminar flow means that the volume flow in each one of these has to move at exactly the same rate. So what this thing is saying is that the change in volume with respect to time must be equal to the area times the velocity. This is what's known as the volume flow rate. So what volume flow rate says, based off of this expression, says that the change in volume with respect to time must be equal to the area times the velocity, which must be equal to a constant. This is what's known as volume flow rate. Because of this expression, what this says then is that the area 1 times velocity 1 must be equal to area 2 times velocity 2. And if I open this up to another tube over here, then I'd have to have the same expression saying that area 3 times velocity 3 must also be equal to area 2 times velocity 2, which is must be equal to area 1 times velocity 1. So this is what's known as the volume flow rate. So it means that the volume change with respect to time is simply equal to the area times the velocity, which is then equal to a constant everywhere along this tube. So that means if I want to know the velocity at 2 relative to the velocity at 1, well, the velocity at 2 is simply equal to the ratio of the two areas times the velocity at 1. So this says that V2 then must be equal to V1 times area A1 divided by V2. So what does this mean? This means if I went from a large cross-sectional area down to a small cross-sectional area, which one would have the faster velocity? I have a large cross-sectional area going to a small cross-sectional area. Which one has a faster velocity for the fluid moving within inside of it? Well, V2, right? Because if this is going from a large to a small, means that this is going to become even a bigger number, which means that if I take that, multiplied by V1, I get a very large velocity. You see this all the time, especially when you go outside, when you have a hose. Initially, if you turn on your hose, has a large cross-sectional area, the water kind of drips out. But then I see Brooke and I say, I want to get Brooke wet, so what do? I cover half of that hose with my thumb. What happens in that case? Water goes flying out, and in this case, because what I've done is I've decreased the amount of area, which means I've gone from a large cross-sectional area down to a small cross-sectional area, meaning the velocity coming out of the water, or the water coming out of the tube, is now much greater, which means I can spray Brooke from here. That's how that's actually needed. I wasn't it. So this is what's known as the continuity equation, or what's known as the volume flow rates. So this thing is also what's known as the continuity equation. Says that the area times the velocity anywhere along this tube must be equal to a constant. It's known as the continuity equation. So we'll pick up from here on Monday. So on Monday, we'll generalize this to something more nasty.
I have a question.
Sure.